Alright, the purpose of this lesson is to explain how, if we weren't able to do the MC delta T calculation in a practical sense, we could still work out the heats involved with reactions. So my example today is the reaction that happens in a Bunsen, because Bunsen gas is normally methane, or mostly methane. It burns completely in the presence of oxygen to make carbon dioxide and water. We've represented those molecules using our molecular model box, specifically so that we could see clearly what bonds were involved. Notice also that representing it this way, we can see the link between what our numbers mean in our equations. That if we've got a 2 out the front, it's talking about the number of molecules, whereas the numbers at the bottom are referring to the number of atoms within a molecule. And we can also see by representing it this way that conservation of mass exists. That we've started with one black, we still have a black representing carbon atoms, 4 whites on this side, 4 whites on this side representing hydrogen atoms, and 4 reds on this side and 4 reds on this side still representing oxygen atoms. That conservation of mass. That the general concept of chemical reactions is that we don't create or destroy atoms, we just put them in different combinations. Now the purpose is to calculate the heat involved with this reaction. We anticipate it's an exothermic reaction because it is a combustion reaction, and we can look at this reaction as taking the 4 reds and the 1 black and the 4 whites, having to break them down into individual atoms prior to putting them together in their different combinations with different bonds. So what we're doing is doing a count of the bonds we have to break over on the reactant side to get them back to individual atoms. And we have 4 CH bonds here within the methane molecule, and within the 2 oxygen molecules we have 2 oxygen-oxygen double bonds. And we can put actual assigned numbers to these bonds using the bond energy sheet over on the left-hand side. So to break 1 carbon-hydrogen bond, we need 410 kilojoules per mole. So I've multiplied that value by 4 because there's 4 of those particular bonds that have been broken. And similarly with oxygen. So I can get a tally for the amount of energy required to reduce these substances back to individual atoms. Similarly, we can look at the bonds that need to form once we've got them back to individual atoms. And I can see 2 types of bonds here. There's a bond between a carbon and an oxygen, and there are 2 of them. And there are 4 bonds between, 4 of these types of bonds between an oxygen and a hydrogen. And similarly, I can get values for these bonds using the reference sheet. So for example, an OH bond, to break the bond between an oxygen and a hydrogen, the value is 460. So adjusting for the number of those bonds and finding a total, we get a value of 3,312. Now at this stage I haven't got signs on them, but what we need to acknowledge is that we need to put in energy, that's a plus sign, to actually reduce these molecules to atoms. And when we release, we actually release energy when we form our new bonds. We've lost an oxygen. So that we're putting signs on our values on our left and right. To find the overall heat of that reaction then, we're just adding those values together. And we get a value of minus 676 kilojoules per mole. Overall minus because that's what we'd expect because it's an exothermic process. Now I put the title of this as an estimate because when we look up the actual value for it in the data book, we get a value of minus 890, but it's still in a ballpark figure. And in some equations it's actually, or reactions, it's impossible to actually do, and they are only calculated theoretically. Thank you for watching.